All the known matter in the universe consists of the following fundamental particles: the up quark and its heavier cousins, each of which has an electric charge of positive 2/3. The down quark and its heavier cousins, each of which has an electric charge of negative 1/3. The electron and its heavier cousins, each of which has an electric charge of negative 1. And the neutrinos, each of which has an electric charge of 0. Each particle has an associated antimatter particle with the same mass, but the opposite electric charge, thereby doubling the number of particles. We now need to double the number of particles again because there are actually two versions of each matter and each antimatter particle. One version has what we call a left-handed chirality, and the other version has what we call a right-handed chirality. The chirality of a particle is related to, but not the same thing, as its helicity, which can also be left-handed or right-handed. The helicity refers to the component of spin in the direction of the particle's motion. For a particle traveling at the speed of light, the helicity of the particle is always equal to its chirality. Massless particles always travel at the speed of light, but particles with mass must always travel slower than the speed of light. The slower a particle is traveling, the less likely there is to be any correlation between its helicity and its chirality. Chirality is a purely quantum mechanical property that has no analogy in classical physics. It deals with what direction the complex numbers describing the particle's quantum state rotate around the complex plane when the particle is rotated around its direction of motion. Gravity, electromagnetism, and the strong nuclear force treat left and right chiral particles in exactly the same way. So from their perspective, the left and right chiral versions of a particle can be thought of as if they are the exact same particle. The only known phenomena in existence that distinguishes between the left and right chiral particles is the weak nuclear force. The weak nuclear force only affects the left chiral version of the matter particles and the right chiral version of the antimatter particles. Only the left chiral version of the matter particles and the right chiral version of the antimatter particles are able to absorb and emit the force carriers of the weak nuclear force, the W and Z bosons. The other known fundamental particles that are bosons are the photon, the gluon, and the Higgs boson, each of which have an electric charge of 0. The Z boson also has an electric charge of 0. But the W boson has an electric charge of either positive 1 or negative 1. Like all other phenomena in the universe, The weak nuclear force obeys the conservation of electric charge, meaning that if a positive charge is created, a negative charge must be created by an equal amount. The weak nuclear force allows a quark with a charge of -1/3 to transform into a quark with a charge of +2/3. And it allows a quark with a charge of +2/3 to transform into a quark with a charge of -1/3. These transformations occur either by emitting a W boson or by absorbing a W boson. A quark and an antiquark can combine to become a W boson. And a W boson can be split into a quark and an antiquark. Provided that the total electric charge is conserved. Note that another property that is always conserved is the difference between the total number of quarks and the total number of antiquarks. Similarly, the Standard Model also states that another property that is always conserved is the difference between the total number of leptons and the total number of antileptons. The electrons' heavier cousins are called the muon and the tau. The electron, the muon, and the tau each have their own associated neutrino. The electron, the muon, and the tau are the charged leptons, and the three neutrinos are the uncharged leptons. The emission or absorption of a W boson can cause a neutrino to transform into its associated charged lepton. The emission or absorption of a W boson can cause a neutrino to transform into its associated charged lepton, or for a charged lepton to transform into its associated neutrino. Unlike the case with quarks, when the W boson interacts with leptons, we actually have three different conservation numbers: one for the electron, one for the muon, and one for the tau. We now know that as the three different types of neutrinos travel through space, they can transform into one another, thereby violating these three individual lepton conservation numbers. However, at the moment of interaction with a W boson, the three individual lepton conservation numbers are still obeyed. Therefore, when a W boson splits into a lepton and an antilepton, either the lepton and the antilepton are both associated with the electron, or the lepton and the antilepton are both associated with the muon. Or the lepton and the antilepton are both associated with the tau. To conserve electric charge, either the lepton or the antilepton must be a neutrino, due to the fact that the W boson has a charge of either +1 or -1. Unlike the W boson, the Z boson has a charge of 0. A Z boson can split into a matter particle and its associated antimatter particle. A matter particle and its associated antimatter particle can combine to become a Z boson. The Z boson can also be absorbed or emitted by matter or by antimatter particles. But unlike the case of the W boson, exchanges of the Z boson do not transform a particle from one kind of particle to another. Both the W boson and the Z boson have an extremely large rest mass. The top quark has a much larger rest mass, but all the other quarks and leptons have a rest mass much smaller than that of the W or Z bosons. Therefore, unless the particle has an extraordinarily large amount of kinetic energy, when any particle other than the top quark emits a W or Z boson, this momentarily violates the conservation of energy. In these cases, the W and Z bosons exist only as virtual particles. The greater the violation of the conservation of energy, the smaller the duration of time for which it can occur, and the lower the probability that an interaction involving these virtual particles will happen. As a result, for all particles except the top quark, interactions with the W and Z bosons are very rare. This is the reason why the weak nuclear force is so incredibly weak. However, this limitation does not apply to the top quark, which has a rest mass larger than the W or Z bosons. When dealing with a top quark, the weak nuclear force is usually the strongest force in existence. More information is available in the other videos on this channel, and please subscribe for notifications when new videos are ready.